Hello, this is the third part of the chapter 5.1, and we can talk about some important properties of eigenvalues and eigenvectors. First, and this is actually kind of a fun theorem, the eigenvalues of triangular matrix. When we work with determinants, we really enjoy working with determinants of triangular matrix because that was just the product of the diagonals. Actually, the eigenvalues of the triangular matrix is equally pleasant. They are just diagonal elements. So for example, for this matrix, it's 3 diagonal elements, 3, 0, and 2 are the eigenvalues. Or sometimes we like to number the eigenvalues. So we can say that lambda 1 is equal 3, lambda 2 is equal 0, and lambda 3 is equal 2. But again, it's just convenience to number them because we can then number corresponding eigenvectors. But overall, it's a really fun thing to do. So if you can get your matrix to triangular form, just your finding the eigenvalues is really easy. Okay, the second property is a little bit less straightforward, but it's related to our definitions of eigenspaces, which we discussed in the previous lectures. If we have several eigenvectors, say from V1 to Vr, which correspond to distinct eigenvalues from lambda 1 to lambda r, then the set of those vectors, V's, are linearly independent. And that's a really important property because it helps us to find a lot of interesting solutions for the matrix equations. But of course, the question is like, okay, that's really nice, but we find that, often there is more than one eigenvector which corresponds to given eigenvalues. Would that be true? So let's look at this question, one specific case. Let's say we have two eigenvectors, B1 and B2, and they correspond to distinct eigenvalues, lambda 1 and lambda 2. And there's also a third eigenvalue, lambda 3, but it has two linearly independent eigenvectors, B3 and B4. So does the set formed by the vector B1, B2, B3, and B4 actually will be a linearly independent? Really not straightforward question. So let's start from the definition of the linear independence. So when there is a linear combination of our vectors B is equals 0, if these vectors B are linearly independent, then all the weights C1, C2, C3, C4 should be equal 0. So let's start with this identity and see if the weights are 0 or not. So, and first two are a little bit simpler, but the most interesting part of this equation is this combination of B3 and B4. And it is a linear combination of eigenvectors corresponding to our third eigenvalue, lambda 3. And by the definition, it should be in the eigenspace for lambda 3, which means by definition of eigenspace, it contains only eigenvectors or 0 vectors. So there is only two distinct possibilities here for our linear combination, and we will label them as outcome 1 eigenvector and outcome 2, 0. Let's explore this outcome and see if any one of them can be true. Let's look at the first outcome. So our linear combination is the eigenvector for lambda 3. In this case, the set of eigenvectors B1, B2, and our new eigenvector slash linear combination is actually a linearly independent set, which is again, for a definition of linear independence, our weights C1 and C2 should be equal 0, and our third linear combination should be equal 0. And that's where we have a problem. Then linear combination of B4 and B3 is an eigenvector. So what we get now is the zero eigenvector, which cannot be possible by the definition of eigenvector. So we have to abandon the outcome 1. It cannot be true. So let's look at outcome 2, which is saying that our linear combination of B3 and B4 is a zero vector. That would also mean that our vector B3 and B4 are linearly independent. In other words, the vectors are linear independent when their weights C3 and C4 is equal 0. That's really nice. So we can come back to our original long linear combination of our set B1, B2, B3, and B4. And since that part in the red box is equal 0, which means that the linear combination of B1 and B2 should be equal 0. And by theorem 2, our eigenvectors form the linearly independent set. So if linear combination B1 and B2 is equal 0, then the weights C1 and C2 must be equal 0, which means that all weights from C1 to C4 is equal 0. In other words, the set of our vectors B1, B2, B3, and B4 is a linearly independent set. And okay, guys, this is quite an extensive derivation, mathematical proof. And starting from this week, we will engage more in this extended proof. So it's maybe not very clear how we're going through this right now, but I would like you to read through the proof several times and then go to the end of the chapter and work through several more proofs.